I should say good morning, good afternoon, and good evening, everyone. And of course, thank you to the organizing committee and the scientific committee for giving me the opportunity to be here. It's really a pleasure. So what I'm going to be speaking about is joint with my colleague, Robert Ream. And so let me start with the setting and motivation for what we studied. So the setting is strictly in 3 dimensions. So you have a Lorentzian manifold in 3 dimensions, and as well a time-like vector field that is distinguished in some way. So this could mean distinguished from the point of view of curvature along the flow of T. Perhaps it could be distinguished as a killing vector field or some weaker condition or some combination of these. So I hope to convince you or persuade you in this talk that if you find yourself in a setting like this, then the Newman-Penrose formalism, adapted of course to 3 dimensions, can be a useful tool. And let me actually give you a reference here. I think the nicest application of the Newman-Penrose formalism to dimension 3 that I've seen is actually in this paper by Nurovsky and Tagavi-Chabert recently, in which they prove a version of the Goldberg-Sachs theorem in dimension 3 using the NP formalism, with the Cotton tensor, of course, replacing the Weil tensor here. So that's a very, very nice use of this formalism, I think. Okay, so what's the basic idea behind the NP formalism, in particular in dimension 3? The basic idea is to express the curvature, derivatives of the curvature, basically everything, in terms of the of the curvature, all of these geometric properties, things, in terms of the flow of T. It's divergence, twist, and shear. Okay, so as I mentioned, 2 types of results can be had, and I will give you examples of both. You can get global results, particularly in the compact setting, and you can also get local classification type results. So I will go to that, but I'll just remind you what divergence, twist, and shear are. So I'm going to normalize my time-like vector field T so that I can define the following well-known map from the normal bundle of T. It's a linear map. Its matrix is as you see, written down with respect to any frame. The anti-symmetric parts and symmetric parts have been separated for you, and I've gone ahead and further separated the trace-free symmetric part of the symmetric part. That's the shear. And the anti-symmetric part, which governs rotation, of course, is called the twist. I've written down the components for you in terms of this frame, but I won't be needing them. All we're going to need is the fact that the shear and the twist are actually frame-independent quantities. In fact, also conformal invariants, so I won't need that fact either. And they describe this kind of behavior associated with the flow. Before I move on to the NP formalism, let me just give you a couple of references to show you that this map is very well known and has been well studied. In the Lorentzian setting, there's work by Romero and Sanchez, who look at the case where D is skew adjoint and are able to obtain integral inequalities. I was just checking my email to see if anyone had emailed me that I'm no longer there. So they're able to obtain integral inequalities involving the Ricci tensor along the flow of T, and their work is in fact in all dimensions because this map can be written down in all dimensions. On the Riemannian side, there's work by Schmidt and Wolfson and others, specifically in 3 dimensions, where they look at the eigenstructure of this map. They use it to write down evolution equations satisfied by the shear and twist, and they study manifolds with what they call constant vector curvature, Riemannian 3 manifolds. So this map is certainly well known and well studied in the Lorentzian and Riemannian settings. How does it feature in the NP formalism? As follows. So let's build that now. The Newman-Penrose formalism in 3 dimensions starts with a frame, and then sort of very much in the spirit of the original space-time null tetrad version, and really for convenience here, we complexify the space-like variables x and y into a complex valued vector m and its complex conjugate, and henceforth work with a complex frame, Tm m bar. Keep in mind that T is not null, it's a time-like vector field, of course. And then one defines really the all-important quantities in the NP formalism, the so-called spin coefficients. In the original 4-dimensional version of Newman and Penrose, there are 12 of these. Here there are only 5, so it's more manageable. Let me just say a bit about these. So the first 3 of them, kappa, rho, and sigma, actually directly encode those properties of the flow of T that I've defined in the previous slide. Kappa, for example, is 0 if and only if T has geodesic flow. You can actually just sort of see that by inspection. If you were to expand the real and imaginary parts over rho, it would give you the divergence and the twist, respectively. And finally, sigma is precisely the components of the shear that I defined for you earlier. But really, to use the NP formalism successfully, these remaining two spin coefficients, this epsilon and beta, are just as important, actually, because they can be modified by changing your frame, in particular x and y, to better suit the geometry. Sometimes this can involve just a simple rotation of x and y. For example, you can always rotate x and y and make epsilon 0. That may not be the best thing to do, however, given what you're studying. Other times, x and y will appear naturally as eigenvectors of the map D in the previous slide. And yet in other instances, you have to sort of solve a quasi-linear PDE, and it's sort of more complicated. But basically, massaging epsilon and beta in the right way is really at the heart of using the NP formalism in dimension 3 effectively, I would say. And when I state a few results for you in just a bit, I'll instead of sketching the proof, I'll just sort of tell you what form epsilon and beta took in our proof for those problems. Okay, so once you have your frame, once you've written out your spin coefficients, the spirit of the Newman-Penrose formalism is to express everything in terms of them. Lie brackets, covariant derivatives, curvature components, derivatives of them. And the nice thing is that in dimension 3, there aren't that many equations. You can actually fit them in one slide. So here they are. There's a lot of stuff on this screen. All I want you to notice is that everything is expressed in terms of our complex frame, T, M, and M bar. And other than Ricci tensor terms, everything is in terms of these 5 spin coefficients, just like in the 4D version, of course. And of course, this is in full generality. There's no assumption on T here other than its unit time life. So then the question becomes, as I've written in red, when does the geometry of what you're studying simplify these equations in an effective way, right? And I'll show you 2 results along these lines. But before I do, I want to just bring your attention to the equation star, just to show you in a simple way, the way that the NP formalism is useful. So if you look at that equation star, you'll notice that other than that Ricci tensor term, every term has either a kappa or a sigma in it. We know that kappa governs geodesic flow. So if your T has geodesic flow, kappa vanishes. And of course, sigma is the shear. So if your flow is shear-free, the kinds of vector fields that you would study for the Goldberg-Sachs theorem, for example, then every term in this equation would vanish except for the Ricci term, which then of course has to be 0. So this equation kind of shows you that there's a direct relationship between the shear of T and the curvature of your ambient metric. And this is the kind of way in which the NP formalism is useful. It gives you sort of direct links between the flow of T and the curvature of your manifold along these lines. Okay, so let me state some results now to end the talk. Remember I mentioned that there are sort of global obstruction type results, and then there are sort of local classification type results. Let me state a global obstruction result. Here it is. Can everyone see this okay so far? I'm still there?
Yes.
Thank you. Thanks for that verification. So here's the result. Pick any compact 3 manifold without boundary M, a positive constant lambda, and pick any function that is not identically 0 but doesn't take the value lambda. Smooth function. Then it turns out there is no Lorentzian metric on M whose Ricci tensor looks like this, as you see, for any unit time-like vector field T. If lambda is 0, not positive, but 0, this can happen, but then your manifold is isometric to basically S1 cross a Riemannian surface. So that's a global obstruction result. Let me say a bit more about it. I think the best way to appreciate this is to actually consider the case that is not covered by this result. Consider the case when F equals lambda. Then you would just get the Einstein condition with positive Einstein constant. And so in dimension 3, we know that's equivalent to constant positive curvature. And of course, we know by sort of a foundational result collectively by Calabi, Marcuse, and Klingler that there are no such compact Lorentzian manifolds in any dimension. And so this result is basically saying that even if you deviate from the constant curvature condition along the direction T, even that's not allowed. Even that's prohibited in dimension 3 in this form. And I'll just point out there actually is no obstruction if lambda is negative. You can actually write down examples on the three-sphere where the Ricci tensor behaves like this for a choice of time-like vector field T. Okay, a very brief sketch of the proof. How does the Newman-Penrose formalism help you to establish this result? How is it useful here? Well, you can imagine it's a proof by contradiction. You would assume this equation holds and then find a contradiction. As soon as you assume this equation holds, of course, T is now a distinguished time-like vector field. And it turns out that this considerably simplifies those equations I showed you in the previous slide. Let me just show you some of the important ones that feature in the proof here. These are all evolution equations in the divergence, in the twist, in the shear, in the function f, even in the determinant of d that actually plays a role here. They're all kind of Riccati equations, equations whose solutions are exponentials, sort of very manageable, very nice ODEs here. And all of them come together, as well as compactness, of course, to prove that not only must T have geodesic flow if it satisfies this Ricci condition, but it must also be divergence-free. And then this fact, this is like the first step of the proof. This fact in turn helps you find the right frame, the right choice of epsilon and beta, in this case, beta. You can find a frame in which beta vanishes. That doesn't always happen because remember, beta is complex, so it has a real and a complex part. So this whole thing vanishes. And you kind of carry on from there in your analysis to get a contradiction. So that's a way in which you can get global obstruction, in which the MP formalism can be helpful. Now let me end with the last slide and give you sort of a local classification problem. This one involves Killing vector fields, time-like Killing vector fields. This is joint with my colleague Robert Bream. So here we give a local classification of metrics, Lorentzian metrics on three manifolds that support a time-like Killing vector field, that admit one, a unit time-like Killing vector field. It turns out that you can always find local coordinates t, r, and theta, and a smooth function phi in which your metric takes this form in equation 2. Of course, to say that it decomposes into a killing part in the quotient metric is not terribly surprising. What makes this an interesting classification for us is that the quotient metric has the Gaussian curvature that you see, sort of given canonically in terms of the scalar curvature and the Ricci tensor of your ambient three-manifold. And also really lifting a result of Kasdan and Warner almost directly. If these coordinates happen to be globally defined, then you can also determine when they'll be complete. This inequality will have to be satisfied. So an example of a local classification type result. The most important thing I want to say about this result is that it's in fact already known. Coordinates isometric to 2 were found by other methods, by Manzano and Lerma and Manzano. They were in fact studying minimal surfaces, looking at submersions over surfaces whose fibers are the integral curves of a Killing vector field. And in fact, they have a formula somewhat more general than our equation 3 here. So theirs is the more general result found by other methods. So finally, how does the proof work here? What is the right choice of epsilon and beta, so to speak, for your NP formalism? Well, it comes as follows. The Killing condition is already quite nice. It simplifies things already, as you can imagine. The shear goes away. The real part of rho goes away. It has to have geodesic flow if it has constant length. And so you use this information to find a frame, it turns out, in which epsilon and beta take this form. And this one is a little more involved. It actually involves a quasi-linear PDE that you have to solve, which is locally solvable. It's okay. And then you, writing the metric in terms of the dual coframe, you kind of build up the coordinate system starting from here. And of course, I'll leave out all those details. And so I'll stop here, sort of a global result, a local result. You're always using this NP formalism to try to work with the right frame, in particular the right choice of epsilon and beta, in the hope that it will simplify your analysis. And I'll stop here. Thank you.